Hello, I'm the mathematical Mr. Daycock, and today I'm going to be introducing you to the concept of calculus. Now, calculus is a very, very important subject that is used in all forms of science at the moment. It's used in biology, it's used in medicine, it's used in chemistry, in physics, in engineering, in electrical science. Pretty much any science you can think of uses this mathematical technique. And we're going to just get started on the very basics of it today. So, a little bit of its history first. Calculus was invented by these two gentlemen. We've got Isaac Newton on the left and Gottfried Leibniz on the right. And they both came up with calculus, but they didn't work together. No. In fact, they very much disliked each other over the fact that they both invented it individually. And each of them fought over who copied the other, and well, in fact, neither of them did. But they came up with this idea, and at its very basic level, it's looking at a problem like this. Let's say we have something moving along. We know it's accelerating. We know its speed is changing all the time. But ultimately, all we can measure is how far it's gone after a certain length of time. So we've taken these measurements after each second, so after, or maybe hours or days, we're not necessarily sure, we're kind of ignoring the units in this case, but after each time unit, we've taken a measurement. So after 0 units, we knew it hadn't moved at all. After a time unit, 1 time unit passed, and it had moved 1 distance unit. Again, this could be meters, it could be feet, it could be miles. That isn't our relevant question at the moment. After 2 time units, it's moved 4. After 3 time units, it's moved 9 units. After 4 time units, it's moved 16, and 5, 25. Now, many of you will probably already at this point be identifying that this is following the squares. And this has been chosen very specifically for this example. Obviously, in real life, it wouldn't be quite as nice as this. But as a very basic example, imagine this was how it was moving. Now, the question is, how fast is it going at any given point? How fast is it going at time equals 1? Now, this isn't actually anywhere on in this data, but at the same time, it's an inherent property of how it goes to each distance. So we just need to ask ourselves, what does speed mean? What does velocity mean? Well, our velocity is equal to our change in distance divided by our change in time. Now this seems like something we can easily calculate because we have this. So at 1, well, it's gone 1 time unit, so our change in time is 1, and it's gone 1 distance unit, so in change in time is also 1, and that gives us 1. So our velocity is 1. But that was considering these 2 bits. There's no reason why we couldn't consider these 2 bits. So we could also say our change in time was, well, the change in distance was 4 take away 1, and divided by our change in time was 2 take away 1, which gives us 3 over 1, which is 3. And why has that happened? Well, it's happened because it's accelerating. Its velocity is changing all of the time. And our key question is, what have we just calculated here? Well, the 1, that is the average velocity between the first 2 seconds. And the 3 is the average velocity between the first second and the second second. So it's the average, and we should probably change that here. We should put average here. And we don't want the average velocity. We want to know specifically how fast is it going at the exact point that our time is 1. How fast is it going here? And this was basically the very start of the problem that these two mathematicians were struggling with. So how do we approach that? Well, what we want to do is get closer. So looking at this, as many of you noticed, really we can probably say that our distance x is equal to our time squared. And this is quite valuable because now, even though we're only taking measurements at 6 points, we could say, well, we're fairly sure that when our time is equal to 1.5, then the distance travelled will be equal to 2.25. And we can be fairly sure of that because 1.5 squared is 2.25. And we can, although we're not certain, we can basically go, well, it looks fairly certainly like this, and so we can make that judgment. And as things go by, we'll get more and more certain about things, potentially, but right now, that's what we're going on. I'm going, well, let's assume that our distance function is this, x is equal to time squared, and that will help us out, because now we can take closer points. Assuming that, we could actually consider this table, time and distance. Well, we know that 1 and 1, we've already got that, but let's consider 1.1 and 1.1 squared, which is 1.21. Working out the time there, well, this is much, much closer to our 1. We were just taking a very small step here, so this is much, much closer to our actual velocity we care about. So if we work out the average velocity here, which is going to be 1.21 subtract 1.1 divided by, and then change in time is 1.1 subtract 1. So remember, this is change in distance, write it as delta, change in x, and this is our change in time. So our change in distance, our change in time. Oh, got my arrow and my T the wrong way around there. Change in time is here. And that's going to be equal to, sorry, that's not 1.1, that's still just 1. That's equal to 0.21 divided by 0.1. And plug it into a calculator, or remember how to divide by decimals, and we end up with 2.1 as our velocity. And that is much, much closer to our actual value of 1, our actual velocity at 1, but it is still an average. It's not the real velocity, it's the average velocity between time is equal to 1 and time is equal to 1.1. So if you want to get closer to 1, we need to just do the same thing again. Let's get closer and closer. So when time, we go from 1 this time, and let's go to 1.01, much closer to 1. And then, so therefore our distance travelled at 1 is still just 1. From this, we're just referring back to our original graph, and we're using the function, or in fact using the function here, x is equal to t squared. And then if t is 1.01, we're looking at x being 1.01 squared, which is 1.0201. And now we can work out the change in x and the change in t again. So our change in x is going to be 1.0201, because that's our final distance. Subtract the original distance that we started at for this time period. And we're going to divide that by our change in time, which is 1.01 subtract 1. And we're going to end up with 0.0201 divided by 0.01, which is equal to 2.01. And this is much closer to, even closer to our actual value of 1. And if you look at this, if you're looking at this, you'll probably go, well, actually, it's looking very much like it's going to be 2. And basically, that's what you would keep doing. You would keep trying it out and keep getting closer and closer with your averages until you got fairly confident that you knew exactly what was going on. Except that that's not quite good enough. Really, we want to have justification for this. As things stand, I'm going to be going through that in the next video, fully justifying how this works, fully justifying that this makes sense. But for now, we're going to take it as the answer to this is going to be 2. And now we know that, we can do that with another one. So what about if we wanted to know the velocity at time equals 3? So let's say we wanted to do it at when t equals equal to 3. Well, again, we could go to the top and go, well, what's the difference between there? Well, it appears to be 4 take away 3 is 1, so our time distance is 1, and 16 take away 9 is 7, and it appears to be 7, but that's the average between these 2 points, not the one at 3. So we get closer to 3, and we're going to start trying things like t and x, we're going to go from 3 to 3.1, which will give us 9 when we square it, and 3.1 squared is going to be 9.61. Working that out, we're going to get 9.61 subtract 9 all over 3.1 subtract 3, which is going to be 0.61 over 0.1, which gives us 6.1. And then we go, well, actually, we want to be a bit closer. Let's be more precise. And we get we're still looking at t equals 3. Let's go from 3, and obviously 3 squared is still 9. And let's go to 3.01, much closer to that actual 3 that we care about. And then from that, we get 9.0601. Plugging that in, we get 9.0601 subtract 9. That's the change in our distance, change in x, divided by our t, which is going to be 3.01. Subtract 3, that's the change here, the change between these 2 points. And that's going to give us 0.06101 even, divided by 0.01, and that is 6.01. And again, in this case, hey, it was looking like it's heading towards 6, and it is. Our velocity at the point when time equals 3 is going to be 6. And we can keep going in this way, and we'll get actually every single one. So if this is our form, our velocity, v, is going to be 0 here, 2 here, 4 here, 6 here, 8 here, and 10 here. And if you're paying attention, you can see that that's actually a very close connection to the time, and we can write down right now that it looks like the velocity is going to be equal to 2 times the time, i.e. v is equal to 2t. And this is the actual right answer. This is the exact answer. All we're missing here, as you can see, this is all approximation so far. What we're missing here is the rigor, the really precise justification that this is definitely right, as opposed to just looking like it's right and trying out lots of values and seeing that it seems to work. We want to justify that if x is equal to t squared, then velocity, if our distance is t squared, then our velocity is going to be 2t. We want to justify this claim. And we will be doing that in the next video. So thank you for watching, and I'll see you in the next video.